Hi, so my name is Joseph Tooby-Smith. I'm gonna give a practice talk, but I'm gonna record it and I'm gonna put this recording on the internet. So this talk is gonna be based on a paper called Smooth Generalized Symmetries of Quantum Field Theories that I wrote with Gripaios and Oscar Randal-Williams, and the arXiv number for this paper is given here. This talk is primarily based at mathematicians interested in physics rather than physics interested in the more mathsy side of things, I guess. So then maybe if you are a physicist watching this, there may be some stuff, some terminology that you don't understand. And if that is the case, feel free to add something in the comments or contact me if you're interested in learning more. Hopefully at some point I will give this talk to a group of physicists or a version of this talk to a group of physicists, and I will obviously record that and put that on the internet as well. So this talk is really going to be based in a couple of different sections. So the first part, really this part here, is going to be based on defining what I mean, or really coming up with a definition of smooth generalized symmetries of quantum field theories in a rigorous formal way. We then have this kind of isolated part, which is going to be looking at an application of this definition. It's going to show this relationship that the physicists often talk about between dimension and the maximum n-form symmetry that you can have for a symmetry. And then I will finish by giving two examples of symmetries or of different constructions, different types of field theories where you can define these smooth generalized symmetries. Everything I'm going to be doing really up to these examples is going to be completely general, though, for any dimension field theory, for any type of background structure. I'm not going to talk about gauging in this recording. I really put this here just in case for when I do this talk live. I run out of time. I have the opposite of running out of time. I've got more time to fill. I have another video where I talk in more detail about gauging. So if you're interested in that, you should see that, and then I will obviously conclude. So let me start with the basic idea. This is like the elevator pitch. Let's say this is the thing. The one thing that if I told people what is this paper about, I will tell them this is what I'll say. Really, this paper is based on an assumption. It is based on the assumption that higher category theory is the correct language to study QFTs. Now, to the audience that is more mathematically orientated, and those of you that know topological field theories, this assumption is not surprising. This assumption is perhaps very natural. It's kind of obvious that this is perhaps the way that things are going to go in the future. So based on this assumption, what I'm going to do in this talk and what we did in this paper is we're going to define invertible generalized symmetries. In this language, so in the language of higher category theory. And I note that I'm restricting to invertible generalized symmetries here. And that is because I don't know how to do the non-invertible case. So I'm going to be talking, when I say generalized symmetries here, I mean like invertible n-form symmetries, invertible two-group symmetries, but they're going to be smooth. So they go kind of beyond the literature in that sense. So before I give you a definition of a smooth generalized symmetry of a quantum field theory in this more rigorous language, I need to introduce two things. One of them will be familiar to those mathematicians who are watching this. Well, both of them will be partially familiar to the mathematicians. So the first part is the cobordism hypothesis. I'm only going to need the easy part of this. And then the second part is really groups and actions in a topos. And then after that, I will define symmetries of field theories. So let me remind you of the easy part of the cobordism hypothesis. I'm going to use both the topological and the geometrical version. Really, implicitly, I'm going to kind of think interchangeably between the topological and the geometrical case here. So in the topological case, the easy part of the cobordism hypothesis says that d-dimensional QFTs with a given tangential structure form a category, really an infinity n category. Let me just put n category. Okay, infinity n category. X defined as the category of symmetric binodal functors from the bordism category, board D, to some target category, symmetric binodal target category C. And the topological cobordism hypothesis says that X is in fact a groupoid. So this is not the full cobordism hypothesis. This is just a part of it. And throughout this talk, I'm going to call groupoids, infinity groupoids spaces. So the geometrical version is very similar. It says that d-dimensional QFTs with given geometrical structure form a smooth category as defined by gradient path law. X, which is in fact, and notationally is kind of defined in a similar way to the topological case, but this is, which is in fact a smooth groupoid. And I'm going to call smooth groupoids in this talk smooth spaces. In other words, X lives in the category of smooth spaces. And I'm going to denote this category. I'm going to denote this category of smooth spaces SM. And this category has, for example, manifolds as objects. It has diffeological groups as objects. It's got things like Lie groupoids, higher Lie groupoids, and all of these sorts of things. So it's a very general category of smooth spaces. It's defined as the sheaf category on the site of Cartesian spaces. And really the cornerstone of this research, the cornerstone of what I'm going to be telling you today, is that SM, this category, is a topos. And you can think of a topos as roughly a category with some internal notion of homotopy theory. It's very rough statement. So we can kind of do the sorts of things that we can do in homotopy theory in a generic topos. One of the things you can do is define like connected objects, truncated objects. You can define groups, actions of groups in a very similar way to how you would for a generic, as you would in homotopy theory. So, okay, that's the first part. And really this is setting up the space X or the smooth space X. And we're going to use the smooth space X to help us define smooth generalized symmetries of quantum field theories. X could be, for example, the smooth space of quantum mechanical theories. It could be the smooth space of 129 dimensional quantum field theories with a given background structure, like mapped to a target space. So let me define groups and their actions. So in a topos, and this is really the second part we're going to need to be able to define a smooth generalized symmetry of a quantum field theory. So I'm going to let X be a topos. And hopefully my notation here is good enough so that you can distinguish between the object X that I defined for the cobordism hypothesis and the topos X. One of them is meant to be calligraphic. So in a topos, in any topos, you can define the notion of a group. And the easiest way to do this without me going into like simplistic objects in this category is to simply define it as a pointed connected object in X. And we will denote these pointed connected objects as follows. And this BG kind of indicates a de-looping of a group G. So examples in this topos of smooth spaces correspond to things like Lie groups, which is good because basically symmetries in physics are done with Lie groups more often than not, basically because you want to do Nervi's theorem, and to do Nervi's theorem, you need the notion of a smooth group. Other examples of groups in this topos include diffeological groups, and these come into play in physics, for example, when you have the diffeomorphism group for manifold. The diffeomorphism group of manifold may not be a Lie group. It is, however, always a diffeological group. And other examples include higher abelian Lie groups. And these are groups, for example, of the form Bn to the A, where A is a Lie group, an abelian Lie group. And obviously, these are what are going to give us higher form symmetries, or smooth higher form symmetries. And everything I'm going to tell you about today, I'm going to keep writing G to be a generic group, and G can be any one of these groups. And if it's this type of group, it will correspond to higher form symmetries. If it's just a Lie group, it will correspond to normal symmetries, and so on and so forth. Oops, erased too much. And obviously, you have things like higher form 2 groups, Lie 2 groups, Lie 3 groups. They are also groups within this topos. Once you have a group, you can obviously define a group action. So you can define in a topos a G action on an object X in the topos. And really, for what we're going to be doing, we're going to take this X to be this X of smooth space, this X corresponding to quantum field theories. So a G action on X is an object X over G to be G. I'm going to say X over G rather than saying like X over G. So it's an object X over G to be G in the slice category X over BG. Okay, the slice category is basically the category of all morphisms from some object down to BG, and your morphisms in this category are commuted to triangles up to B, and then so on and so forth up the ladder. So subject to the condition that if you pull this morphism back, and the topos pullbacks are defined, if you pull this morphism back along this base point, you get back X. And this is a pullback. So that's the definition of a group action. And this definition corresponds to exactly the definition that you would see in homotopy theory. So if you're familiar with the definition of homotopy theory, this is exactly the same definition translated to group actions. So in this topos of smooth spaces, we can let G, for example, be a Lie group. We can let X be a manifold. And if we do that and we ask what are the group actions, they obviously correspond to the group actions of a Lie group on a manifold in the usual sense. In other words, maps G cross X to X such that the multiplication rule of G is obeyed, etc., etc. Another example of great relevance to what I'm going to be talking about today is when G is a Lie group and X is BH, where H is some Lie group. And this corresponds, and the group actions in this case of G on BH correspond to short exact sequences of Lie groups of the form H to G hat to G. So once you have a group action, you can ask what are the fixed points of that action? What are those points that don't get moved around up to homotopy? So really this is homotopy fixed points rather than just the normal fixed points. So if we have one of these actions defined up here of a G action on X, a fixed point is then just a section of this map X over G, or X quotient G to BG. In other words, it is a map from BG to X over G such that the composition is the identity up to homotopy. So if we take this first example of a G action on a manifold, the fixed points basically correspond to ordinary fixed points of a group action. On a manifold. And if we take the second example of a Lie group G acting on a BH, where H is also a Lie group, we're going to basically get back splittings of the short exact sequence. And we will find that the splittings of the short exact sequence will give us back like representations, and it will give us back things like group actions or projective representations. So really, we are now in a position to define symmetries of field theories. And the definition is going to basically merge this idea that we have this object X and these notions really of a fixed point of a group action. So it's perhaps kind of obvious what the definition of a symmetry of a field theory is going to be. So let me just write it out. Completely, a QFT equipped. So the notion of a fixed point is actually a structure rather than just data. So we're going to say equipped with a G symmetry with respect to the action, to a given action, so to the action X over G, and X here really is the space of field theories, which our field theory belongs to, over BG with respect to an action on X is a homotopy fixed point. It's a homotopy fixed point, or just a fixed point, as I call it above. Homotopy fixed point of this action. Good. So let me do an example. Let me do the example of a topological field theory. So the topics that we're going to be working with is spaces rather than smooth spaces, but we can really do this in smooth spaces if you wanted to. So we're going to take 1D TFTs, in which case X is BGLN. And really you should think of this as a discrete group. If you take the trivial action, so the trivial G action on X, in other words, the action that doesn't do anything, the homotopy fixed points are G representations are n-dimensional. N-dimensional G representations. Really, I should have a co-product here over n, but I'm just going to focus on one n. And this kind of makes sense. So a one-dimensional topological field theory can just be thought of as a quantum mechanical system with an n-dimensional Hilbert space where you don't have unitarity. And your Hamiltonian is a zero Hamiltonian. So obviously in this case, your symmetry is just going to be n-dimensional representations of G. There are no other conditions that you could possibly impose on it. Excuse me. So in the second case, sorry, so if for a non-trivial action, for non-trivial reaction, we can get back things like projective representations. And we also get back things like semi-linear representations and so on and so forth. Okay, so that's kind of like the most basic example of this definition of a symmetry of a field theory. So this kind of like draws a line onto this first section. It kind of like ends our discussion of the definition of the smooth generalized symmetry of a field theory. If you let G here be a higher form symmetry, one of these B entities, so you're going to get back the notion of an invertible higher form symmetry. That's in the physics literature. So this really covers a broad range of symmetries. So I'm now going to introduce another way that one could possibly think of defining a symmetry of a field theory. And I'm going to do this using this character called Simplicio. So Simplicio was taken from one of Galileo's books. And Simplicio, in our case, is going to define a symmetry of a field theory in a different way to how I have defined it above. And what you should be thinking is that Simplicio is defining a symmetry of a field theory in a way that we kind of expect the physicists are implicitly doing it. So Simplicio is a character, and Simplicio is going to have the trait that Simplicio has a favorite I cannot spell favorite, but pretend that's his favorite. A favorite theory. So they have a favorite point in this space of field theories 1 to x, and they only care about the symmetries. So care only about the symmetries of that field theory. So they don't care about the symmetries of field theory in X, in this space of field theories X, or the smooth space of field theory X. That's totally like the other side of the space to their decide field theory. They only care about that one field theory. And Simplicio is going to define kind of in a similar way to how I have defined it here. Simplicio is going to define a symmetry of this field theory. So how are they going to do it? The first thing they're going to do is they're going to take a connected cover of X. So they're going to take an object x0 which factors this map 1 to x, and this object x0 is uniquely defined by the fact that you enforce this right hand map to be -1 truncated and this left hand map to be -1 connected, and those have definitions within a topos. So this defines this connected cover. I might call it the connected component of this object x, of this map x throughout this talk. And instead of finding group actions on x, what Simplicio is going to do is they are going to find actions and fixed points of x0 rather than x. And often this is a lot easier to do. So obviously, if you're focusing on one field theory, you don't have to worry about the whole space x. You just focus on this little connected component, which contains your field theory, and you find the actions and the symmetries on that instead. And this is what Simplicio does, and we kind of think this is more akin to what the physicists do in the literature. So let me give you an example. Let me give you an example where X corresponds to unitary quantum mechanics. I'm not going to tell you how you get the space of unitary quantum mechanics, just I'm going to tell you some facts about it. It's basically, it corresponds to a Lie group void. So Simplicio is going to have a favorite theory within the space X, and this corresponds to a choice of Hamiltonian X And then in this case, the connected cover is BSH, where SH is a subgroup of UN, assuming they're working with n-dimensional on an n-dimensional Hilbert space, such that M is in SH if and only if it commutes with the Hamiltonian. And this is not something I've defined. This is something you get for free given this smooth space X and a Hamiltonian, the choice of a point in that smooth space. So you kind of already get, you can already see where you're going to get like representations that commute with the Hamiltonian from. So for the trivial G action, you would indeed do. So this is a trivial G action on X0 now, so not on the whole space X. You do get back reps that commute with H. Just ordinary unitary representations that commute with Hamiltonian H. For non-trivial G actions, you get back things, for example, like projective representations. But there is a problem. And there is a problem that kind of shows, it's going to show you why I haven't defined things, my symmetries, as the way that Simplicio has. Why I've defined it with this whole space X, rather than just focusing on a specific theory, a specific point in that space. And the problem is most easily demonstrated with an example. An example is, let me take the Hamiltonian 1 minus 1. So it's a very simple Hamiltonian that you get in quantum mechanics. And I'm going to take my G, my symmetry, to be said 2. And there is an action. So actually, let me say that in this case, BSH is just BU1 plus BU1. So in other words, this connected component X0 is just BU1 plus BU1. There is an action of GX, or G can act on BSH, roughly by taking e to the I theta, e to the I phi, to minus, sorry, e to the I theta, e to the minus I phi. So it basically does a complex conjugate on one of the components and not the other. And the problem is that this symmetry is allowed and that this symmetry has fixed points. Sorry, this G action is allowed and this G action has a fixed point. So in this case, Simplicio would find a symmetry related to this action. And this is a problem because from a physicist's point of view, this action is pathological. It corresponds, or the symmetries would be pathological. They basically correspond to taking time reversal on half of your Hilbert space, but not the other half of the Hilbert space. I think that's a useful way to think about these sorts of symmetries. And obviously, you shouldn't be allowed to do that in quantum mechanics. And the idea, and this is really an issue for Simplicio, and I can show that this is an issue for Simplicio by showing that this action falls foul of what I'm going to call a smoothness anomaly. So let me define a smoothness anomaly, which is kind of telling us a way that how, or kind of the relation between these two definitions, the definition of a smooth, the definition of a symmetry as I've defined it, and the definition of a symmetry, how our friend Simplicio defines it. So imagine you're given a symmetry of a field theory in the way that I've defined it. So imagine you're given a G action on X with a fixed point. And that fixed point, as per my definition, corresponds to a symmetry, a field theory equipped with a symmetry. And let's say this is through X. So in other words, we would kind of say that the underlying quantum field theory here is field theory X. So a G action on X with a fixed point through a point little x, lowercase x, gives a g-action on x0 with a fixed point. So in other words, you can go from my definition to Simplicius's definition. If I give you a symmetry, Simplicius will also find a symmetry. So to show this, let's break down what I've given you. I've given you, first of all, a g-action on x, and obviously x corresponds to the smooth space of quantum field theory, so of a given dimension and a given background structure, geometric structure. So the first part is I've given you a symmetry on x, and the second part is I've told you that I have a homotopy fixed point, a map bg to x over g, such that the composite is the identity. And I've said this goes through x, which basically means if I pull this map back, I get the map x here. Now, the trick is that you take a Postkanoff decomposition of this vertical maps here. And Postkanoff decompositions preserve pullbacks. So I get basically a diagram of pullback squares of the following form. So if I take the Postkanoff, let me actually just start with this map here. I take the Postkanoff decomposition of this map. I get x0 by definition. I'm going to take a Postkanoff decomposition at a given level. And obviously I just get one there, BG, fill in my group action down the bottom. And if I take the Postkanoff decomposition of this map here, I'm going to get some object. It's guaranteed to exist. And I'm going to call that object basically x0 over g for an obvious reason. So all of these squares are pullbacks, all of the right angles are pullbacks. So from this, I get a pullback diagram. I get a g-action on x0 with a homotopy fixed point. And the homotopy fixed point basically corresponds to the same homotopy fixed point that I found. So let me recap. If you take a g-action, a field theory with a symmetry, in the case that I've defined it, Simplicius will also find that g-action with the symmetry. So you can kind of go from my method to Simplicius's method of defining things. But the point is you cannot go the other way. So not every g-action with fixed point on x0 extends to an action on x. And this kind of makes sense. And when this occurs, we're going to say you have a smoothness anomaly. So this kind of makes sense, right? If you take like a space and you restrict to a subspace and you find a group action on that subspace, it's not necessarily always true that that group action can be extended smoothly to the whole space X, even if you have a homotopy fixed point. And this is basically this notion. Now here's the key fact that these smoothness anomalies basically get rid of these pathological examples, these examples up here that they've gone. So an example of a smoothness anomaly is basically this example where H is 1 minus 1 and G is equal to Z2. Okay, so this kind of shows that there are two definitions, the two possible ways to define a symmetry of a field theory. That's my way and the Simplicius way, and that Simplicius way falls foul to this problem that you get these pathological examples. And this is resolved by the fact that these examples have smoothness anomalies. Okay, so that kind of ends, we've kind of like defined a symmetry of a field theory. I've given you enough way to define it, Simplicius way, and I've told you the incompatibility between these two things and introduced this notion of a smoothness anomaly. So I'm going to kind of change track right now, and I'm going to give you an application of this definition. And that application is this relationship between dimension and n-form symmetries. And as you can, I'm going to preempt this, as you can see, we're also going to need to refer to Simplicius's method. Basically, because we're going to be talking about a statement that physicists make, and as I've said, physicists often, we think that Simplicius way is kind of the way that physicists think about stuff, even though it has these pathological examples. So The physicists say the following. If you speak to a physicist that works with generalized symmetries, you will often hear them say the following, that d-dimensional theories have at most d-1 form symmetries. So what do I mean by it's kind of a vague statement? So let me tell you what I mean. And to tell you what I mean, I need to introduce the notion of truncation. So for any topos, you have a map tau n, which takes your topos back to itself. And this map essentially gets rid of higher homotopy groups. So in a topos, you have a notion of homotopy group, and this map basically truncates your objects so that all of the higher homotopy groups are set to the identity. This is the same as truncation in homotopy theory. And really, given a group, we can think of pi n, the nth homotopy group of a group, is really the n form part of the symmetry. So what we kind of want to show is that to show the physicist statement is that if you have a G action on X, you can replace this with a truncation of that G action, an action of the truncated G up to the d-1 level. And the same holds, and you want to show the same holds for the fixed points. So let me give you a theorem. For a generic topos, for X detruncated, and if this is the space of, or the smooth space of quantum field theories of d dimensions, it will be detruncated. We have the following. So we have a diagram, a commutative diagram of the form for every G action. So given a G action, we have a commutative diagram where we can truncate this G to the deep level. And this square happens to be pulled back, and this square happens to be pulled back. Or they happen to be Cartesian. And the same kind of holds for homotopy fixed points. If you have a homotopy fixed point of this, you can replace it with a homotopy fixed point of this right-hand side. So this is saying that if you have a G symmetry, you can replace it with a symmetry of the deep truncation of G. But this is not quite what the physicists say, because for the physicists, you would want d-1 here, not d. So we can give a refinement of the physicist statement, which says that d-dimensional theories considered collectively have at most D-form symmetries, and they do have D-form symmetries. And this is really easy to show because if you take zero-dimensional field theories, X forms a set, and you have a group action. You have a knot group from. You have a knot from symmetry. You have an ordinary group actions on sets, and that would even contradict the physicist statement taken in its naive configuration. So really, we can refine. So we can ask, how do we get back the physicist statement that D-form theories have at most d-1 form symmetries? And the way to do this is to not look at symmetries through the way that I defined it, but to look at the way that Simplicio has defined it. So in this case, Simplicio wants to find symmetries not on X, but on X0. And this is detruncated for d-dimensional field theories, but it is also connected. And because of that, you can show, I'm not going to prove this, but you can show that in this case, if you take a G action on X0, this corresponds to the pullback of an action of the d-1 truncation of G. So in this case, we do get that a G symmetry can be replaced by the D minus 1 truncation of G. And a similar statement holds for the homotopy fixed points. So really, the second refinement is that D-dimensional theories considered individually have at most D minus 1 form symmetries. And I kind of have illustrated here that you can just show this basically using theorems of group actions. And this is kind of where these statements come from. So let me give you some examples. I now want to change track again. I want to give you some examples. In other words, I want to choose a specific X, and I want to give you an example of group actions on the X and the homotopy fixed points of the group actions and properties thereof. The problem is that X is the full space X is actually hard to come by. And this is why Simplicios method is actually kind of useful. So although I said Simplicios method has these smoothness anomalies, actually doing things Simplicios way can be kind of useful. So I'm going to take some X's that correspond to different types of field theories. I'm not going to prove that the space that I'm going to give you actually corresponds to the actual space. I know Grady and Pavlov in their papers have a few different X's, and he's kind of motivated by these. So let me do the example of 2D TFTs, and we can either think of this as in the smooth space or in the topological case in the topos spaces. So either one will work for this example. So we're going to let X, in this case, is basically the coproduct over N, although I'm going to ignore the coproduct. I'm just going to focus on one N of C star to the N, B2 C star. So CX is basically the multiplicative group of complex numbers, and we're going to take N copies of that. So we're going to take N, and we're going to, this is an abelian group, it's an abelian Lie group, or a discrete group in the spaces case. So we can take the twice the looping of that. And there's an action of Sn on this, the permutation group of degree N, and that obviously just permutes the factors. And really, this really corresponds, we should think of this as corresponding to two-dimensional topological theories with a target that has objects which are algebras, morphisms which are bimodules, and two morphisms which are intertwiners and appropriately smoothed out in the smooth case. So for such field theories, there is one unique point. So there's one, this basically space defines a unique field theory. It's unique up to homotopy. And what will be important later is that this theory very roughly assigns to the cobordism corresponding to the circle, it assigns the bimodule Cn. So it's very hard. Really, what I would love to do here is go, okay, we have this smooth space X. Here's given a G, here's every possible symmetry, every possible G action you can have on X, and here's every possible symmetry that you can have. I can't do that. It's very hard to say anything like that completely generally. So what I'm going to do is kind of give you some facts. I will talk about the n=1 case, and I will tell you what you can do with each of the actions. So let me give you, first of all, some intuition of the G actions in this case. So imagine we are given a G action. So we're given a G action on this space X. I'm just going to call it X, but I really mean the specific X that I've given you here. What one can do is take a Poskanov decomposition. So you can take a Poskanov decomposition of this space here, and you get the Poskanov decomposition of this map happens to be BSN. And basically, the Poskanov decomposition of this map, we get some action basically at the Poskanov decomposition at the the one truncated, one connected factorization system in this case. So we get a G action on BSN, and all of these squares are pullbacks, and obviously the whole square is a pullback as well. So this tells you if we have a G action on X, we get a G action on BSN. And if we have a homotopy fixed point of this action, we're obviously, so if we have a map from BG down to here, we're obviously going to get a map from BG into this thing here. So for every symmetry of a field theory in these cases, we get a G, or basically a representation, a twisted representation, depending if this action is triple or not, a twisted representation in Sn. And how one should think about this is that this representation acts on this state space. So basically we have a map, okay, let me call this representation R, and this basically acts on this Cn, map Cn by the corresponding permutation. So for every symmetry of a field theory, okay, it's kind of, maybe I said this in a bit of a messed up way, but for every field theory equipped with a G symmetry, so every section of this map, you get back a twisted representation acting on your state space, is kind of what I'm saying here. So as I said, it's very hard to say anything in general. So a case that perhaps is quite easy to look at is the case when X is equal to, when N is equal to 1, and then X is just BC star. Oops. Siri wants to speak to me. Okay. So in this case, X is BC star. And what we're going to take, what I'm going to tell you in this case is that the fixed points have a very specific meaning. So if you take a generic action on X, a generic action of G on X, the fixed points in this case correspond to degree 2 C star cohomology. And this is really just by definition. With coefficients in the local system given by the G action. So this is really kind of relates these in this n=1 case, relates the fixed points to cohomology. We'll see later a different relation to cohomology. In the case when G is compact, the space of homotopy fixed points, a compact Lie group, the space of homotopy fixed points in this case become the sets of cohomology G R plus single cohomology and degree 3 cross with degree 3 single cohomology or G for coefficients instead. And if instead of a G action, you have a BG action, so this would be a one-form symmetry. So the one-form symmetries in this case correspond to, or the homotopy fixed points correspond to homomorphisms of G and C star. Okay, so this is kind of an example of the n=1 case. I told you the fixed points here correspond to degree 2 cohomology with coefficients in the local system given by G. When G is compact Lie group, the fixed points for the trivial action, this is the trivial action. The homotopy fixed points correspond to the set of cohomology. And when G is a one-form symmetry, the fixed points just correspond to homomorphisms from G to C star. So that's the first example. It kind of shows you the sorts of things that you can do with these cases. So let me go on to the second example, and this will be the last example before I finish up. So we're going to take the d=1 case. And in this case, the space X is basically the space B nebula GLN exponentiated by m. So this is the mapping space from maps, or the points of this really are maps from M to B nebula GLN, and then your morphisms are, like homoscopes between these maps, etc. And these maps M to B GLN correspond to principal, by definition of this binebula GLN space. They correspond to principal GLN bundles on M with connection. So again, it's very hard to say anything completely general about the fixed points of the space, but one can say the following. One can take an action either on this BGLN or on M, and that will give you an action on X. So one can take an action on BGLN, and this gives an action on X with a multiple fixed point, basically given by M to, or from maps from M to the smooth space of multiple fixed points of this G action on this BGLN, B nebula GLN. So this kind of is saying that if you have an action on this target space, you can find an action on the whole thing, and then your multiple fixed points kind of obey with that action. Are basically maps from M to B nebula GLN, that multiple fixed point space. And you can do the same with the source. And this really is a very important example, because we often think of symmetries and field theories in the traditional sense when you have Lagrangian as acting on some sort of like target space if you have a sigma model, and this kind of corresponds to this sort of thing. So you can have an action on M, and this gives an action on X, and then multiple fixed points of this action correspond to maps M over G to B nebula GLN. In other words, you quotient your manifold by G, and in some cases, if M is a manifold and G is, sorry, I should say M is a manifold. We think of M being a manifold, okay? And G is a Lie group. In certain cases, this may also be a manifold. It may not. And really what this corresponds to is equivariant differential cohomology. So these maps are basically maps in equivariant differential cohomology. And one can play some tricks with this, and it's useful to show that you can actually play these tricks completely in general. So you can take this sort of G action, a G action defined in this way, and you can map this. So this is a G action in the smooth space, and this corresponds to equivariant. The fixed points of this correspond to equivariant differential cohomology. One can take this action and one can map it down to spaces. So one can take manifolds and map them down to their corresponding sets. One can take Lie groupoids, map them down to their corresponding underlying groupoids. We're going to call this map gamma. And we can get an action on just the underlying smooth space by the underlying group, by the underlying discrete group or topological group in this case. So this is B gamma G. And if one can also play the game of truncating this map. So one can take gamma X and one can truncate this. So I'm kind of talking about this in general, but really we should think of this as the case of a G action on X through the manifold M. And the important thing is, or the interesting fact so this is also a group action in S, is that the multiple fixed points of this lower action here, the truncated action, correspond to invariant differential cohomology. And one can also, so this kind of shows that you have a map from equivariant differential cohomology to invariant differential cohomology. You take the multiple fixed points of these actions and you map them down in a very similar way. And then you can also map these down to just differential cohomology. Okay, so this kind of concludes the last example. I realized I am almost at an hour of this talk. So let me conclude by giving some future directions. So I said I'm not going to talk about Gaussian in this talk. I have previous talks where I talked about Gaussian, basically saying the similar stuff to what I was going to say here anyway. So there are some future directions that I want to look at. The first is to ask, when do smoothness anomalies occur? So I've kind of given you an example of a smoothness anomaly, but I don't know how to say anything completely generically. So when do smoothness anomalies occur? The second further direction for further study is to generalize basically everything I've told you to non-invertible symmetries. The third is to look at Nervous theorem. So to ask the question, you know, okay, now we have smooth symmetries, a notion of a smooth generalized symmetry in a very rigorous way. Can you generalize this to study Nervous theorem? And the second is to look at Gaussian in the smooth case. Okay, and there is no fifth point. So really, what is the conclusion of this? The conclusion is very simple, that one can study invertible generalized symmetries in a formal way and recover many well-known results. And we kind of recover, this is the expectations. So this kind of concludes my talk. If you have any questions, I know my handwriting went stocky towards the end, and perhaps I didn't explain these last two very clearly. But if you have any questions, feel free to contact me. My email address is on the corresponding paper, or feel free to put them in the comments below. And yeah, thank you for taking the time to watch this talk. And now I have the awkward bit where I try and work out how to stop the recording.